14th session of the part 1 of this series of lecture. So today, in this session, we will focus on a very relevant algorithm called empirical mode decomposition, or EMD. This algorithm was proposed back in 1998. And if you take a look, that is the snapshot I took about 2 days ago. So just imagine this number of citations. Okay, how many citations do you have? Think about it. Maybe over your whole night, your whole life, right? All the papers, you cannot achieve even 1/10 of this citation, right? So it's a very influential and impactful algorithm. And actually, this is the algorithm that drove me to study mathematics, to switch from medicine to mathematics. So it's a very interesting algorithm, and I will tell you what it is, so that you have a basic understanding. Okay, so this is an overview of the EMD algorithm. Essentially, there are two parts. The first one is called EMD, okay, empirical mode decomposition, and there is a lot of loop and the rules, which I will explain to you one by one in a bit. The second part is after you get the signal decomposed, you run something called Hilbert spectral analysis and get the time frequency representation. And the basic idea will be once you get the intrinsic mode functions, CLO, LO's intrinsic mode type function, you run Hilbert transform, and you get analytic form of the IMF function. And then you take the amplitude modulation function and the phase, and you generate the time frequency representation in this way. Okay, and this is what you get. So if you pay attention, you will see that the whole algorithm is actually in a reverse order of what we have discussed so far, like synchronous squeezing, short time Fourier transform, and so on. In short time Fourier transform or synchronous squeezing, what we did was we generate time frequency representation first, and we use information inside to achieve the decomposition. But in this EMD algorithm, we get decomposition first and generate time frequency representation. So that's a basic overall big picture relationship. Okay, so let's take a look at each part, EMD and the Hilbert spectral analysis. The EMD part is actually an iterative algorithm, which is a bit, maybe looks a bit complicated, but if you think about it, it is very natural, and I will use pictures to illustrate the idea. The basic idea is you have the iteration 1, 2, 4. This is called the sifting process. Sifting process. And you repeat this sifting process, which you can view as an inner loop. You get one intrinsic mode function, IMF function. And then you subtract the IMF function and iterate the sifting process. And the whole process 1, 2, 6 is called EMD. The step-by-step idea is the following. You have input function x, then you identify all extrema, and you do interpolation to get upper envelope and lower envelope. And you find the mean, which is the mean of the upper envelope and the lower envelope. Then you extract the detail. What is detail? You can imagine that this mean will be a low frequency component. So you do a subtraction, you get the high frequency component. Usually it is called detail. Then you iterate 1, 2, 4 on the detail until the detail has satisfies some stopping criteria. For example, it's 0 mean. And once you repeat it many, many times, so that the detail satisfies some criteria, like a 0 mean, then this D is called the intrinsic mode function. And you subtract this intrinsic mode function from our input signal, you get M of t. And then you repeat 1 to 5, the iteration sifting process, on the residual m by setting x to m and run 1 to 5. And to get the second IMF, and you repeat, get third IMF, get fourth IMF, until some stopping criteria is achieved. For example, when the peak frequency is low.
Yeah, sorry, you mentioned several times repeat. So roughly how many times?
It depends on the signal.
Oh.
It depends on signal. So you need to set up some stopping criteria, and it depends on the stopping criteria. Then you see how many times you need. And in the very end, you output multiple IMF functions and the residual. So that is the overall EMD algorithm. And there are some algorithmic details. For example, how to do interpolation. The proposed one is using cubic splice. And if you have boundary effect, how to solve it? Usually use mirror symmetry. And stopping criteria, there's what is the mean zero. Then there are some thresholds you can set up so that you can say, well, it is already what we want. And you can find the MATLAB code online here. And you will see there are a lot of variations of EMD algorithms, a lot, really a lot. Okay, we will not go into all of them. I want to show you show you the algorithm using this example. So you have two components. One is the tone, this is harmonic function. Another one is a chirp, which has frequency low in the beginning and high in the end. Now you have tone plus chirp. This is the summation. Okay, and we want to ask if we are able to decompose this signal into the desired components, or do whatever we want. So what we do, as I mentioned before, was this is the input signal. We find local maximum, and we generate the upper envelope by cubic spline. We can find local minimum and generate lower envelope. And then we find the mean. And we do the subtraction. So this is a residual. Now if you look at this residual, it looks okay, isn't it? But it is actually not good. It's not good in the following sense. This is 0. And if you pay attention, this is not really a nice oscillation. It doesn't oscillate very regularly across 0. It sometimes has larger trough, sometimes it has a smaller trough, and so on. So this is not good. Okay, so the shifting idea is, how about if we iterate this upper envelope and lower envelope procedure? So let's do it. We take this one, find upper envelope, lower envelope, and mean. And do the subtraction. Now if you pay attention, it looks better, isn't it? It is more even, upside and downside, more even. But it's still not perfect. So let's repeat again. Upper envelope, lower envelope, second iteration. Yes. Now you get again another mean, and you correct it. Right? And we repeat it. Third time, fourth time, fifth time, you see iteration, fifth, sixth, 7, it's getting flatter and flatter. 8, good. So we get the first IMF in the end, because the mean finally satisfies some 0 stuffs. So we do the subtraction and we get residual. From this residual, we continue to get the second IMF. So we do the upper envelope, lower envelope, mean, and we get residual. Okay, and we can update it. Okay, finally we get the second IMF. It's almost like mean 0 stuff. Good. Now we can continue with the third one, IMF 3. iteration is 0, right? And the iteration 1, iteration 4, that's what you get. Finally, iteration 8, iteration 12. Very nice. Now it's like flat. So this is the third IMF. Now we can continue with the fourth IMF. But before that, you may see, hey, it seems to have too much oscillation and so on. But don't worry too much. If you pay attention, the magnitude is now minus 0.1 to 0.1. Its amplitude is very small, actually. So it has some oscillation, but it's very small. And you can continue with the fourth IMF, the same, right? Fourth IMF, which is oscillates slower and slower. Okay, this is the fifth. And this is the final result. Now, the y-axis right now are on the same scale. So you can see the first IMF, the second IMF, third, fourth, fifth, sixth, and the final residual. So this is the EMD decomposition, which to some extent you may say, oh, looks nice, right? You get a chirp, you get a tone, and there will be some kind of small residuals. Good. Yes, it works in this case. So in the end, what you get will be X will be the finite numbers of IMF and the trend. And again, the number of K depends on the starting criteria. In some cases, K may be gigantic, and sometimes it may generate or lead to some artifacts or whatever. I will show you some examples of it. This is the first part of the algorithm called EMD, Empirical Mode Decomposition. The second part is Hilbert Spectral Analysis, HSA. So what you get is, this is the input, and you get 3 components. And what you do right now is you apply Hilbert transform for each IMF function, and you get the magnitude and the phase. And now you use the phase to generate the location of the instantaneous frequency and the magnitude to show what's going on of the oscillatory strength. In this case, we have 3 components, so this is what you have. Okay, looks okay, right? And it's quite pretty, isn't it? A lot of fluctuation, not bad. Good, so that is actually the overall. It looks convincing, and actually it has a lot of applications in many, many fields. As you can see, there's almost 30,000 citations, so people are using it. However, to our knowledge, it is intuitively correct, but it is very ad hoc. So there are many parameters you can fine tune so that you can get different results. So far, we have little mathematical understanding. Later on, I will tell you one existing mathematical analysis of this algorithm under simple model. And even under that very simple model, you can already see a lot of interesting nonlinear phenomena. And that will be the topic I will go into. But in general, we do not know what's going on. So far, we do not know. A lot needs to be done. It's a very interesting mathematical problem itself. I want to show you some examples first on simulated signals. And in these simulated signals, we have all ground truths. And you have already seen them in the synchronous squeezing transform, our time frequency analysis tools. So you can see the relationship or what's really going on. So the first one is called mode mixing. So I give you 2 components, okay, and this is summation. And I want to run EMD on this signal and to see what's going on. And this is the result. The first IMF is the red curve. The second IMF is again the red curve. So what do you see? You see something funny, isn't it? It catches the high frequency component very well on the right-hand side. A low frequency component on the left-hand side is considered as the first IMF. And the mode mixing part is somehow decomposed successfully, but they are all organized in the wrong way, organized in the wrong way. So in this sense, the IMF information is a bit misleading because you forget the dynamics, or the dynamics is kind of perturbed. And this is the whole EMD result. You can see first one, second one, very nice, and nothing else. All the others are very, very small, which you can ignore. So in this sense, it is not bad, right? It's only just some missing, some mixed order stuffs. So if you pay attention to its Hilbert spectral analysis, you can see, quite okay. Why? Because on the right-hand side, these two, the red curve and the blue curve, they are the true instantaneous frequency of these two components. So in this sense, the recovery is not bad. The recovery is not bad. But just if you look at the signal itself, you see some weird deformation. So in this sense, Hilbert transform does help to recover the spectrum. And the combination with EMD is good, although in the IMF decomposition you get some crazy mix-up. And you can also try, hey, the HSA is a bit spreading, right? A bit fluctuating. So how about if we just combine, replace Hilbert spectrum by some time frequency analysis tool, for example, synchro squeezing, and this is the result. You get you run synchro squeezing on each IMF function, and you get the resulting time frequency representation of each of them, and you do the superposition. So which tells you it's not bad, but you can see there's some mixing, some confusion here. You see there's a tail, right? This tail comes from the mode mixing because the IMF EMD artificially generate one extra component here, which actually should be this guy as one component. Okay, so that is some kind of troubles that may lead to some misinterpretation. And now I showed you this using this signal to show you the Hilbert spectrum. But this signal is actually generated from these three signals, which you saw before. In these three signals, the instantaneous frequency are very nice. We know everything. But this is a Hilbert spectrum. So what you see is, well, it doesn't really capture what we want. It is very different from the true instantaneous frequency. It oscillates too much. So what do you think? It may be not super informative. Another issue is actually wave shape function, and from my perspective, this is a big issue. If the oscillation is non-sinusoidal, then actually EMD process will get confused. For example, you see these three signals that we saw before. They oscillate slowly in the beginning and end, fast in the middle, and amplitude increases, right? They all have the same behavior. The only difference is the oscillatory pattern, the wave shape function. And this is the wave shape function, the first IMF, second IMF, and third IMF of this guy. Why? Because you can only find local maxima here. So it doesn't really tell you anything. You get to the first IMF. Now, if you consider this guy, the second signal, you have a lot of local maxima, right? And so if you link everything, this is what you generate. IMF 1 is something, well, this blue one. IMF 2 is this higher, lower frequency one. But IMF 1 has frequency which looks weird. And the third one, like before, you get some decomposition. But it's difficult to really say what's going on. What is captured by EMD? That'll be the question. And another example of wave shape function. Now I give you three components. They are all oscillatory, and as I showed you before, the oscillations are not sinusoidal. You sum them together, this is what you get, and this is a decomposition. And you can see the decomposition, which this plot is not very good, but as you can see, the decomposition is weird. It's difficult to say which one is which. So let me zoom in and find the best fits for you. for example, this period, you can get decomposition that seems to fit the noise frequency in a reasonable way, not perfect. You see, there is a missing bit, but all the others follow is good. But the other parts is really difficult to determine which one is which. So the decomposition is totally irrelevant to the ground truth, totally irrelevant. How about Hilbert spectrum? Maybe Hilbert spectrum can give us some information. Unfortunately, challenging, very challenging. Okay, and this is a synchronous squeezing transform of the original signal, which gives you the ground truth in some sense. And this is kind of weak of this component. And if you combine, you apply synchronous squeezing to each IMF, still it is challenging to say which one is which, isn't it? This one is kind of relatively well recovered, but this blue one, I don't know what it is, and this red one is difficult to say. So it is kind of challenging. EMD seems to fit cosine function to the signal, but we don't know what's going on. Again, there's no theoretical analysis. We don't know what's really going on. And that is an impact of small perturbation. I just put some small perturbation in the middle, and this is a ground truth signal, and this is the result. You can see there are some very interesting, huge fluctuation, even trend. So that after decomposition, that is what you have. Weird. And this is the Hilbert spectrum. And you see that if you take a look at the Hilbert spectrum, you see there's a lot of dominant low frequency component by the trend, which masks everything. And if you only take the top 3 IMF and evaluate the synchronous squeezing and do a superposition, you can get somehow reasonably well instantaneous frequency, but not perfect. And this is synchronous squeezing of the original signal. And you can see there are some boundary effects, which I mentioned before, and we'll come back to the boundary effect later. And there are some applications to real-world data that we know physiologically. For example, this is the airflow signal, and this is the mode 1, mode 2. Seriously, it's hard for me to do the interpretation of what the decomposition gives us. It's difficult. I don't know. This one seems to generate some respiratory frequency, but there are a lot of intermittent, weird stuffs that I cannot do interpretation. And this is a PPG signal. The PPG signal on the left-hand side doesn't have dichrotic notch. On the right-hand side, there's dichrotic notch. So the decomposition on the left-hand side and right-hand side have very different behavior, very different behavior. And there are a lot of mode mixing in the middle and in the end even trend. So it's very difficult to do the interpretation. And if you take the top 4 IMFs to run Hilbert spectrum, that is what you get. The 10, that's what you get. Again, the heart rate should be about 1 Hertz, but yeah, I don't know. I just cannot do interpretation. And this is the original signals short-time Fourier transform, which is good enough, right? Heart rate and artifact. But if you put use a short-time Fourier transform of IMF, you get a lot of artifacts, which is difficult. And the synchronous squeezing, again, artifact. There are a lot of strange lines here. What are they? Hard to say. So EMD works, but it tends to, generate something that we do not know how to interpret, and because of the lack of mathematical foundation, so far at least I don't know how to do too much of it. In the very end, I will tell you some theoretical support of EMD and one very commonly applied variation. The theoretical support, to my knowledge, is done by Patrick Flangin in France in 2008. And the model is this guy. You have a high frequency component, which is a cosine. Then you have low frequency component, which is A cosine 2 pi f t plus phi. F ranges from frequency 0 to 1, and A ranges from frequency from minus 1 over 100 to 100. So we want to study the relationship in between these two signals, in particular in the time domain, because we need to find local maxima. We want to say, okay, under which condition you can find the correct local maxima, local minima, so that you can get the signal decomposed. And the quantification C is this guy. Okay, ideally the top one should be the high frequency one. So if you can get a high frequency one successfully, you subtract the true component and then divide it by the high frequency component. Then see what you get. So on the right hand side, that is the result. So which tells you there is a very, very nonlinear relationship. Very, very nonlinear relationship. Very, very nonlinear relationship in between amplitude and the frequency. The main theory tells you that if A times F is less than 1, okay, then the average number of extrema per unit length will be 2. That is, the extrema rate is exactly the same as that of the high frequency component. That is, you can do some nice recovery. But if AF squared is greater than 1, then that is 2 times F. That is exactly of that low frequency one. But what happens in between, we don't know. It's very complicated. This is the main theory. Again, it is still many open problems. For example, how about more components? What about the frequency changes? What about noise? We have no idea at this moment. Okay, there are some empirical explorations people found, very interesting ones, which leads to some variations. The first one is you just input white noise to an EMD. What do you get? Okay, you run 10 times 50, and you evaluate the power spectrum of each component. Then you see very nice, beautiful spectrum behavior. And they all look like kind of Gaussian. Okay, and you can see this kind of separation is a bit like diatic separation in the frequency domain. So, well, it has some seeming like nice property, but how to really, quantify it, we don't know. And it also has some explorations about what about if you don't stop in the shifting, you just continue to shift it many times, never stop. What will you get? What will you get? And they claim that you will get something by module. Well, that's just exploration, which is interesting, which just tells you there are some nonlinear impact on the algorithm. Okay, so I will tell you one variation called EEMD, or empirical ensemble empirical mode decomposition. The idea is very, very simple. It says the following. So given a signal X, now I generate a new signal by adding white noise. Which sounds weird, right? You add white noise? Yes, you add white noise. You make it noisy. And you run EMD. You get some decomposition. And you add many times, many different white noise. They are all independent. And in the end, you get many decompositions. And you order all the IMFs and you do average. And that is the final corresponding IMFs. So the basic idea is you use noise to perturb the structure in some hypothetically existing solution space. And hopefully, after the perturbation, because of the nonlinearity, once you take averaging, you can get something very nice. But again, no theoretical support. We don't know what's going on. In this example, actually, it performs quite well. You see, this is the signal I showed you, right? There's some artifacts in between. And after a decomposition, you see, hey, you can get the signal relatively well back. Although there are some kind of, maybe mode mixing or something. But no matter what, you see, this guy, the artifact, has been very successfully decomposed. So it's very nice. Okay, because this kind of signal, this sudden shock, is considered difficult in general. And this is in a simulated signal. As you can see, what I showed you before, and on the right-hand side, it seems to be, well, okay. You see the first component, very nice, right? But the second component is kind of less clear what's going on. And if you have noise, then, well, to me, I really don't know. It's difficult to interpret. And this is the airflow signal. And as I showed you before, right, it's hard to interpret. On the right-hand side, it is also difficult to interpret. In particular, this part, it is okay. But what's going on in the middle, well, may not be perfect, right? And the interpretation is okay, but, well, challenging. And this is another example of instantaneous heart rate. An example I showed you about a patient waking up from the general anesthesia. Now you can see the third mode, fourth mode, fifth mode. After and the first two modes are noise-like. You can see this part seems to be the respiration. And what is this part? Okay. Anyways, it's difficult for me to interpret. But recall this result. What I showed you before, you can very well see the dynamics, everything. And there's an alternative name of EMD plus Hilbert spectral analysis called Hilbert-Huang transform. And there's even a book called HHT. I just want to remind you who is David Hilbert. You can easily Google it. I don't need to mention who is Hilbert. So I don't recommend to use HHT, which is improper. And to be honest, EMD rings the bell of deep learning. And I put these slides 2016, and this is 2017. I remember, and this very interesting comic that it's on the website. I will not comment too much on this. You read it, and you can interpret what's going on. Okay, so that is for today. Thank you very much.